Okay. Alright. You were given a zero-indexed array nums consisting of positive integers. You can choose two indexes, I and j, such that I does not equal j, and the sum of the digits of numbers of I is equal to that of the sum of the digits of the number nums I is equal to that of nums j. Return the maximum value of nums I plus nums j that you can obtain over all these possible indexes that satisfy the conditions. Okay, max sum of pair with equal sum of digits. Pairs ij that satisfy 0, 2. Both numbers have some digits equal to 9. Oh, okay. 9, 9, 1, 4. 1, 4, 7. Okay. Okay, let me think about this for a minute. Oh, there are no two numbers that satisfy the conditions. Okay. And are we guaranteed to have only one pair? Probably not. We can probably have multiple pairs. So, let me think. This is doable. Hash map. Probably hash map. Okay. Ooh. How am I going to calculate the sum of the number if we can have up to a 10-digit number? That's actually not terrible. Okay. Oh, we just have to return this. Okay. So I'm thinking initially I'm going to iterate through all of these values. I'm going to calculate the sum of the digits. And then I'm going to put it into... I'm going to calculate the sum of the digits and put it into a hash map that has the sum of the digits as the key and a priority queue as the value. And then I'm going to put in the actual numbers in the priority queue. So, and then I'm going to iterate the hash map, take all the values that I can, and then pop the first two. Pop the first two within the priority queue, and then keep track of the maximum as I iterate through them. Okay, so I'm going to have an output integer, and then I'm going to make the hash map that has integer as the key and the priority queue that stores integers as the value. And I'm going to call it what should I call it? Digit sum to value. Digit sum to value. Yeah. Equals new hash map. And then we're going to iterate through each number. Take the current number, and while the current number is greater than 0, I'm going to keep track of the digit sum. So I'm going to take the digit sum and add the current number mod 10. And then I'm going to take the current number and mod equal 10 it, or divide equal 10 it. Beautiful. And then once I have the digit sum, I'm going to take digit sum to value and put in, oh wait, no, I'm going to check if digit sum to value contains the digit sum as the key. And if it doesn't, I'm going to create that key. Is this the best way to go about it? Let me see if I can do something. Digit sum dot. Yeah, that's not gonna work. Okay. So I'm gonna put in it the digit sum and a new priority queue. And then I'm gonna take the digit sum to value, get the current digit sum, and offer the current number. And I actually want all these heaps to be max heaps. So I'm going to do this and make it a max heap. So now we have a hash map with all the digit sums and each number that it belongs to. So then we can iterate through the hash map. I'm going to do for map.entry integer priority queue integer entry in digit to sum, digit sum to value dot entry set. Priority queue integer queue equals entry dot get value. Instead of queue, I'm going to name this sum or values. So if values dot size is greater than 1, I'm going to keep track of a sum and I'm going to say sum plus equals values dot poll, and then the output is going to equal the max between itself and the current sum. And here I actually need to run this twice, but I can just duplicate this. I was thinking about looping, but we really just need to do this twice. And I can do like, yeah, and then I will return the output. Okay. And if the output equals 0, then I'm going to return -1. Otherwise, I'm going to return the output. Yeah, something like that. Beautiful. Oh, nice. First try? Okay, let's think about optimization. So this uses a space complexity of O of n, where n is the number of numbers. Yep. Time complexity here is O of n, but we also do this offer, which I believe takes log n. Yeah, log n. So this is n log n, and this is at worst n. So this occurs in n log n because of this. Now let's think, so the only bottleneck that we can, or potential bottleneck that we can get rid of is the usage of the priority queue. So if I get rid of the priority queue and I just keep a list, I would have to loop through this block to be able to find the two largest values, which would increase our complexity to O of n squared. So we don't want to do that. So the only way I can optimize this is to think about, or the only way I can optimize at least my current implementation is to change, not to change, to it's to structure the value in a way where it's already sorted. How can I do that? I'm not exactly sure if there's a way that, there's nothing at the top of my head that I can think of where I can do that. So let's potentially think about restructuring the problem as a whole. Yeah, actually, oh, this occurs, I take it back. This is not n log n. This occurs in n, but this is also a lot of time complexity. So this, the overall time complexity would be O of n times m, where n is the number of numbers, and m is the average length of each number. And that we can't reduce that bottleneck because we have to be able to determine the value of each number, or sorry, the digit sum of each number somehow. And I'm unsure of a method that we can do that in that is less than the length of the number itself. I'm sure there's some bit manipulation thing that can occur, but yeah, I'm pretty happy with the implementation here. I am unsure of any other ways to optimize other than sorting. Okay, sorting probably would have yeah, sorting would have done something. N log n. Okay, so this is actually faster. Priority queue, that's what I did. Oh, n log m. Oh, n log m. Okay, what could I have done? How is this not n log n? That means this must be n log m. Oh, m is less than 10. It's a constant. I see. So I'm chilling. This is n log n. Yeah. Is this priority queue? I want to see how they implement the priority queue. What the heck? This is way too complicated. I feel like it was a lot more intuitive. Okay. See, that is that is a good question. See, it's hard enough to make me think, but it's not easy to the point where I'm just like typing things out. That was a beautiful question. 60% acceptance rate, kind of high though. Maybe it's just too easy. Wait, how did it handle the -1 situation? Also, let me ask GPT if there's a way, like if this is like super optimal. Is this optimal? No way they do it in linear time. Oh my gosh, what is happening? Is this linear? Oh my gosh, it's linear. Wait, what? Yeah, it is linear. Wow. I guess it's not that much overhead. I'm kind of curious how fast this will be. Yeah, significantly faster, but not. I mean, n log n is not much slower than n, so. I need to look up like priority queue offer time complexity. I'm pretty sure it's O or login. Same with poll. I don't know why I even do this. Login. Okay. It's good to know. I don't think anything below this is easy, I guess. Okay, to find the kth largest element in the stream, I'm going to have a priority queue that is a min heap, and I'm going to add the numbers into it and get the kth item of it. And to optimize it even further, actually, what I can do is I can have a priority queue that has a size of k, and anytime I'm going to add numbers into it until I hit k, and then every time I encounter a new number, I will add, or I will check if that number is bigger than the top of the queue, and then I will add it to the queue and remove the top. And through that, yeah, I can keep track of it all. So I'm gonna make a public priority queue. I'm just gonna call it queue. And then here, I'm gonna say this.queue equals new priority queue. And it's gonna be a min heap. And I'm gonna put k in there because we want to be able to, we can reserve size for the priority queue by doing that. And then I'm gonna say for int number in nums, this.add num. And then here I'm gonna say, actually I'm gonna add another instance field where I have the capacity, and I'm gonna say this.capacity equals k. So I'm gonna check if this.capacity or this.queue.size equals or is less than this.capacity. I'm just gonna offer the current value to the queue. Otherwise, I'm gonna check. I'm gonna check if the value is, or sorry, the top of the queue is less than the current value. If it is, then I'm gonna take the queue and pull the top, and then take the queue and offer the value, and then I'm going to return the top of the queue. Perfect. So add will occur in log n because offer occurs in log n. Peak is O of 1. Poll is O of 1. So all of this is log n. And then the initialization of the queue will take however long. It'll take n log n. N log n, where n is the number of numbers in the array. And it has a space complexity of n. This is for the smashing the stones. Yeah. Yeah, so what I'll do is I will add all the values into a priority queue from the stones. And insofar as the priority queue has a size greater than 1, I will continue smashing the stones together. So I will take the top two values of the priority queue, and I will find the absolute value between the differences of them, and then I will re-add that to the queue until I either have no stones left or 1 stone left. Or actually, I'll always have 1 stone left, I think. Yeah. So here I'm going to make a priority queue, store it with integers. I'm just going to call it queue. And I want it to be a max heap. So I'm going to set the comparator to flip. And I'm going to say for every stone in stones, I'm going to offer the queue the stone. And while the queue's size is greater than 1, I'm going to smash. So int smash equals queue.poll minus queue.poll. And we actually don't have to calculate the absolute value because we're calculating the max already. The priority queue is already sorted, so there's no need to worry about the non-commutative properties of subtraction. Yeah, and then through that, I'm going to offer the queue, smash, and then I will return queue.peak. Yeah. Cool. So the space complexity of this is going to be O of n, where n is the size of the number of stones. And the time complexity of this is going to be n log n, where n is the number of stones. Because here, offering all the stones to the priority queue, the loop takes O of n, and the offer method takes log n. So this block is O of n log n. And pulling these values is O of 1, and offering is log n. But we're navigating the queue size. You're navigating more than the queue size, to be honest. So if we do the math on it, it'll be this runs queue divided by 2 times. So if we use big O notation, it'll just round to O of n. This will run O of n times, but this occurs in log n times. So this is also n log n. So you have n log n plus n log n, and we can reduce that to n log n. There's one graph problem that I wanted to do. what is it? A graph problem? It's a. Is it this one? It is this one. Okay. So, this is similar to that like delete island problem on Algar Expert, I think. But our objective here is any O that is touching the border, we want to ignore all that O and every O adjacent to it. In terms of like north, south, east, and west, up, down, left, right. And then every other O we want to turn into an X. So what I'll do is I will run depth first search for looking for O's on the border, and I will turn each O into a flag, basically. I'll call it like B or I, or it could be anything. B for border, sure. And then depth first search will be run on all the O's connected to the border, and then every other O after that, so depth first search will be run on every O that's connected to the border. And after that, I will iterate through the entire grid, and if the value is a border value, I will ignore it. And if it's an O, then I will convert it, because I know that O is not touching an O that is adjacent to the border. So yeah, what I will do is I will calculate our rows, which is board.length. I will get the number of columns, which is board 0.length. And that should be it. Yeah. So I'm going to iterate through the rows. Int row equals 0. Row is going to be less than rows. Row plus plus. And I'm going to run DFS on the current row, the first column, and I will pass in the board as well. And then I also want to run DFS on the first row, but the last column, so calls -1. And then I want to pass in the board. And then we want to do the same for the columns. So int call equals 0. Call is going to be less than calls. Call plus plus. And I want to run depth first search on sorry, this is wrong. Row. There we go. I'm going to run depth first search on the first row and a variable column and the board, but also the last row. So rows -1, the variable column, and the board. And all this DFS will take care of isolating the border O's that we are looking for. So I can go ahead and write that right now. It's going to be a public. I can make it private. I don't think it matters. We'll have public void DFS, the row, the column, and the board. So the first thing we want to do is check if because we're running depth first search, we don't know what's on and off the board. So we want to check the boundaries of the board. So we want to make sure row and column are greater than 0, but also less than the constraints of the board. So if row is less than 0, or column is less than 0, or row is greater than or equal to board.length, or column is greater than or equal to board.length, I'm going to return and just suspend execution there. Furthermore, if the current value of the board, so board, row, column, equals an X, we don't really care about it. If it equals a border element, like so, if it equals a B, then we don't really care about it either. So we are going to return to make sure that we don't infinitely iterate. And now, after all that validation, we know that we are at a position that is on the board and that the board is an O. Because our three options are X and O, and then the variable that we have introduced, which is AB, which stands for border. So I'm going to change the board, the current position of the board, or sorry, the current cell of the board to be a B, and then I'm going to run DFS. So I want to run it on the current row value plus 1, the column, and the board. I'm going to do the same but minus 1, and then I'm going to iterate on the columns. Call minus 1 board. Okay, perfect. So these 4 lines, they make sure that we navigate up, down, left, and right, no matter what the position we're in, insofar that we pass all of this validation. So after running these 2 blocks of code, all of the border O values and their adjacent values will now be B values. And the remainder of the O's that are not attached to the edge of the board will still remain as O. So what I'm going to do is I'm going to iterate throughout the entire board. Rows, row plus plus, for in call equals 0, call has to be less than calls, call plus plus. I'm going to iterate through each position, and I'm going to say, okay, if the current value of the board equals an O, I want to make it an X. So I'm going to set it to an X. Otherwise, if the current value of the board is a B, I'm going to set it back to O. And then I'm going to return the board. Actually, do we have to return it? No, it's void. So yeah, this is the algorithm. Oops. Perfect. Oh shoot. I can't even see what is wrong with this. What's wrong? The first value? This isn't being covered. Neither is this or this. I'm so confused. Oh, these are X's when they should be O's, not O's when they should be X's. Okay. Is there a reason why this should be an X? Or is there a reason why? Oh. I wasn't in bounds. So the problem that was happening there was that it was registering, it was limiting the columns at the row length, not the column length. So it seems like it was just cutting it off short. So this should pass now. Beautiful. Now what? I need to check something. Oh shoot, I need to respond to this email. Okay. Oh man. Dang.
Okay, I'm wasting time. This is difficult. I need to check something on my phone. I'm going to turn this off. What the heck? Give me a second. Okay, cool.
I got what I needed. What is the... Oops. Oh, shoot. What are the syntax issues? Oh my gosh, why is it freak out like this? Can you stop freaking out? Oh my gosh. See, this is... I don't know if that's much faster, to be completely honest. That's pinching for pennies at that point. Okay. This is the one that I want to understand. Oh my gosh. It's happening again. Oh my gosh. Never mind. Brother. If count is greater than count is greater than num. If count is greater than num. Remove the excess occurrences. If count is less than. Otherwise, if count is less than or equal to num. What's greater, the count? What's smaller there? Okay. Remove 1, add 2, add 1. How does that work? 1, 2, 1, moves needed 3. 1, 2, 1, moves needed 4. That makes sense. Mm-hmm. One move. Um. Okay, I see. So to solve this, basically, we calculate the frequency of each number, and then we iterate through each number and its frequencies. Right here, we get the number, we get the frequency. If the number is if the frequency is greater than the number itself, we want to add the amount of add to the amount of moves the surplus. Otherwise, that's the wrong code. Here, otherwise, that's also the wrong code. This needs to be moves plus equals math.min num minus count and count itself, because we need to take into account just removing the number as a whole. Okay, yeah.